So, sir, our main job would be to select the inputs so that we get those equivalent kind of structures, right?
Yeah, you can do that.
Yes.
Okay. So now, as we were saying just now, that if I have a if I have an inverter which is toggling at say VDD by 2, what am I saying? That on the low side I have this kind of region where output will not toggle, and on the high side I have this kind of region where again output will not toggle. It is in this region that I would not know, or in fact, you could say over here, between here and here. It is in this region that I do not know where my output is. Are you able to see this? So this is called as logical high input range and logical low input range. And the output, as we said, will always go to either VDD or ground. So logical low output range and logical high output range. That when the output has risen to, let us say, 80% of VDD, we say it is high. We don't really need it to be full VDD. And this difference between them is called as noise margin. Okay. And if we have a skewed gate, this gate would either go here or here, and because of which noise margin of one side may reduce, noise margin on the other side would increase. Because what would happen? The output would still high and output low range would still remain the same, but input intermediate range would shift up. Let us say like this. So what has happened? The noise margin on the high side has reduced, whereas that on the low side increases. Are you able to see this? Any questions?
So what is the significance of this noise margin?
Okay, we were talking about crosstalk. What will crosstalk do? It will generate some small pulses here and there, some glitches here and there. So you do not want your outputs to keep toggling for every little glitch. So that is what this noise margin prevents. It saves power. So noise will now not bother your circuit. Your outputs will not unnecessarily toggle because of noise.
So my input has to be has to be above this noise margin, or it can be in this noise margin as well.
So यहाँ पे देखते हैं. So in this case, my input can actually be in this noise margin, and I will still consider it as logical high. That is what the definition of noise margin is. My output will remain here. That is the strength of my gate. But this is additional margin that I'm giving. That even if my input is slightly lower than my output high range, I will still be able to consider that as 1.
Okay, sir. So that if output of one gate is fed into another, the noise cannot and noise get overlapped with the output.
So let us look at it like this. I made a very good output curve over here. I followed this. Okay. Now in between, I had some coupling capacitance coming into picture with another wire, and therefore by the time it reached here, my output fell a little. I was giving an output high of this. Its output was high, but it fell a little. So it came to this level. Now for this particular inverter, I would still consider it as a high signal. So whatever crosstalk this wire introduced into my system, it did not spoil the logic level. I had sufficient noise margin. Noise introduced by this adjacent wire did not change my output.
Okay, sir. Got it, sir.
Okay.
Sir?
Yes.
Okay. Sir, I'm still not getting this point. Like, if we have input greater than that C region, then the output will be low. तो यहाँ पे भी तो वही intermediate के ऊपर है अगर हम, then the output will be, I'm confused, I'm a little bit confused in this.
So the second curve on the curve on the right side, or the representation on the right side, is input characteristics, because हम second inverter के नीचे बना रहे हैं ना, उसके लिए वो input कितना आएगा. So दोबारा से सुनो. My first inverter gave the outputs of logical high and logical low, like whatever is drawn.
Yes, sir.
Now in this long path there was some crosstalk.
Yes, sir.
We added some noise.
Okay.
How much noise can this crosstalk add, or 10 other reasons could be adding noise, है ना?
Yes,
How
sir.
much noise can be added that my second inverter still considers it as 1?
Okay.
So that is my noise margin high.
Okay.
Similarly, on the low side, if I had this first inverter giving an output 0, how much noise can this crosstalk add so that the second inverter will still consider it as 0?
Okay. So ideally क्या होना चाहिए था?
ऐसा ही होना चाहिए था.
हाँ, तो फिर इसको noise क्यों बोल रहे हैं? बस that is my doubt.
क्योंकि ये noise रास्ते में add हुई ना, I have become insensitive to the noise that got added in the process of some other output reaching my input gate.
Okay. हाँ, okay. Now it is clear.
I have become insensitive to that noise. That is why it is called noise margin.
Okay, sir. Okay.
Because if more noise would be inserted, then I do not know what my output would be. Okay. Yes, Raghav.
So in this picture, I would say the left one is the characteristics of the left output characteristics of the first inverter, and the right one is the inverter of the characteristics of the second inverter, right? So, but like I wanted to ask, for a given inverter, if this intermediate region, the area, for example, if we consider this area itself, this would be fixed, right? This can only shift up and down.
Yeah. No, right? Not exactly. Depends on technology and voltage of operation.
So because right, as per my current knowledge, like the voltage, but that would be using for different inverters, or that would be same. So sir, like even this, if we change the beta ratio, then this either I will get the noise margin increased on the high side or the low side. So one has to compensate on the behalf of other. There will be some loss. So sir, like this region then has to remain constant. But
no, that is an assumption you are making, Raghav. In the previous slide, we simply said that this region will go up or low. I did not really say that this region will remain constant also. For example, look at this curve. In this curve, this region is this big, at least.
Yes, sir.
But look at this curve, the original one. This region is probably smaller. So how would this region change? I do not know. There is no way to clearly tell it based on some model or some analysis. See, if you will actually have to analyze the inverter on your CAD to see exactly क्या हो रहा है.
So actually, I was making the deduction based on the fact that, for example, if I'm able to change this area, this transition area, then I can have gains on both the low side and also the high side also.
So typically, if you skew it, this indeterminate region would probably increase. Because what happens is, so look at this. Either Diwali slope hai, this goes bad.
Okay. So like in that kind of situation in which I gain on both sides, that cannot happen. So
that may not happen.
Yeah.
That you will probably be able to do if you increase the voltage of operation.
Yeah.
Okay.
So generally you are saying, sir, that this beta ratio affects this in that the area increases. So like the degradation has to be equally more amplified than if you would have not been there. But it's a shifting also, because in shifting also.
I'm not saying that also, Raghav. I simply said I do not know what to say about indeterminate region. It can increase, it can remain constant, it could reduce. It depends on the technology and voltage of operation and what kind of skew you are talking about. That's all that I said.
Okay.
Sir?
Yes.
Sir, so can you please go back to the previous slide, sir, once? Yes, sir. So, sir, in this graph, suppose we are taking VDD by 2 at the center point, and the graph is the same, beta P by beta N equal to 1. So, in that, sir, noise margin is something that's that we are giving the flexibility towards the top side and the bottom side, right, sir?
So the top side, we are calling it as noise margin high. The bottom side, we are calling it as noise margin low.
Okay. There is no relevance. We don't call the between area as any kind of noise margin or something.
No.
Right,
you see that is where NMH and NML.
Yes, sir. Okay. Thank you.
Yeah. So how to maximize noise margin? Yes, Meher?
Yeah, can you go back to the previous slide, please? Noise margins.
This is also on noise margin only. Tell me.
No, I mean the last one. Yeah. So here on the top we have indicated VDD and on the bottom ground, but according to the inverter characteristics, this top one should indicate when we say logical high input range, we mean that the range of inputs for which the output will be logical high, right?
No, logical low.
Logical low.
Inverter, inverter will invert. Logical high input range, it will convert to logical low output range.
So what's this? What's the logic of subtracting your output range from the input range?
So यही तो बताया था ना. देखो, let us say both are identical inverters. ठीक है? This inverter gives its output based on this output characteristic.
Yeah.
The output, when it starts from here and reaches the input of the second inverter, there is crosstalk in between, which introduces noise.
Okay.
Now the inverter at its receiving input stage considers a much wider range as logic high.
Right.
So what does this mean? That this much of noise, NMH kind of noise, can be accepted from crosstalk or any other reason.
Okay.
That is why it is called as noise margin.
Right.
Okay. I'm just clarifying. So I'm just clarifying a statement. Like we have this noise margin, like this much noise we can tolerate, and if the noise is greater than this, then the operation will be hindered. Am I right, sir?
We do not know what the output would be.
Yeah. Okay.
Yeah.
Okay, sir. Thank you.
Okay. So I know these many questions because we want to increase the noise margin. So how do we increase the noise margin?
Sir, we can make beta P equal to beta N so that our curve goes steep at a point so that we would have a good noise margin on the top and the bottom.
Yeah. So if beta P is equal to beta N, that is how we can do it. What is now? How do we first? Before that, we need to see what is really the noise margin. Should I start to call noise margin from here until here, or from where to where? So a typical definition that is used is that in this transfer characteristic, the points where I have a unity slope from 0 to 1 and 1 to 0 side, those are the intermediate region is called as the region between that is intermediate region, and I have the remaining part as noise margin. Is that okay? So you will get VOL and VOH from this curve, and VIL and VIH also from this curve. So now I will be able to identify what is the noise margin for this particular gate.
So like in short, we are saying that when both the devices are in saturation, we exclude that area, and then remaining
Yes.
is noise. Yeah.
Yes, you can say that. Okay. So having looked at this and having also talked about transient analysis a little while back, we understand that DC analysis is what happens to V out if Vin is constant. Transient analysis is what happens to V out if Vin changes over time. And we also discussed already that the same kind of characteristic will stay valid. You just need to time, you just need to put A, B, C, D, E along the time axis. Okay, we already discussed this in the last class also. This is just kind of summarizing it. But when we do that, there are different figures of merit which would also come into picture, and that is what we need to look at. Okay, so what we are saying that at time t equal to t naught, my input is toggling, and my output was VDD at time t less than t naught. How would my output change after time t equal to t naught? And you notice C load starts to figure in now. We already discussed in the last class in response to one of your questions that why did we not consider C load in the transfer characteristics? Because it is the input outputs are not changing, so capacitance is not valid. However, in a transient analysis, we know that V out is changing over time. Therefore, C load starts to figure in. What will be the impact of C load on the current waveforms? Any ideas?
Delay, sir.
Current waveforms.
Sir, high current spike.
तो वो तो पहले भी हमने करंट स्पाइक की तरह ही दिखाया था.
Sir, more amount of current would be sinking now.
More amount of current would be sinking. तो कहाँ से, यहाँ से कौन सा करंट बढ़ेगा?
सर PMOS से भी ज्यादा सोर्स होगा और NMOS से भी ज्यादा सिंक होगा. क्योंकि
Why would? Okay, so if I'm transitioning from 0 to 1, my output should be going from 1 to 0. Why would PMOS be sourcing more current now?
Sir, in case of the reverse logic, because now more
No,
time
we're talking about 0 to 1 transition only. We're talking about 0 to 1 transition only, Abhi.
Okay.
In this slide, we're talking about 0 to 1. You're talking about response to a unit input. Huh? So 0 to 1 transition aapne diya. What is the response to that? So my question is, how will the current change?
So we are talking here about step response, right?
Yes, response to the step input. This step input.
Sir, I think at the edges where this changes, there would be a bulb. I'm like, there would be a U-shaped curve going high, then it's rises, and while fall it will go down.
Abhi we falling pe nahi ja rahe, Vaishnav. We are only looking at input rise.
Then it will go at a bulb at the edge at which the value is 1.
So I'm asking about the current curve.
So maybe the curve will be more wider because there will be more charge stored in the C load. So the I versus T graph will be more wider rather than a peak.
Okay. So what is being said is that because there is a load over here, this would prevent any change in output voltage. This will resist any change in output voltage. It will start to sink its own charge so that output doesn't change. And therefore, my delays would increase, and therefore, this curve would become wider. Is that what you want to say?
Yes, sir.
Okay. And anything else would happen? So, see, in the transfer characteristics, we said IDN is equal to IDP. Can we say this here?
No, sir.
Transfer characteristic, this was always the case. Can we say the same thing here?
No, sir.
Why?
So As I can think, so for example, if we have no control of V changing as we have applied. So if V is changing, so I know that for this particular time of period, my PMOS will be on, my NMOS will be on. But this V out, I think, is because of C load. Because of this, I think I'm not able to say that what time my PMOS will be in linear or saturation. So these kind of the current, I think I won't be able to say. Sometimes this PMOS will be linear and NMOS will be saturation, and this current is also going. So I mean, sometimes I think that maybe the PMOS could be driving more current to the C load. And
see, let us look at it very simply. Just if we know the output is going to be 0 now, we know that this capacitance has to discharge.
There will be a capacitor current, sir, actually.
So this capacitance, the charge that this capacitor has to be sunk to 0.
Yes, sir. Yeah.
So the NMOS will finally sink more charge than the PMOS.
Yeah.
So the NMOS current has to be, or either the duration of the NMOS current or the amount of NMOS current, whatever we talk about, has to be more than the PMOS current.
Yeah, during that transition also, right? Because
so IDS cannot be equal to IDSP. IDSN cannot be equal to IDSP.
Yes, sir.
In fact, it could be something like this only, that there is a PMOS current which also comes, but PMOS current closes. NMOS remains in the saturation region for a little longer. It discharges the capacitor and then enters into the linear region. So this could be, the first curve over here could be IDSP, and the second curve could be IDSN. Are you able to see this? So NMOS remained in saturation for a longer period so that it would sink the charge from C load. This region should be able to give you the charge stored on C load. Are you able to see this?
Yes, sir.
Yeah. So the power will definitely increase. This area will definitely increase. Yeah.
Because this region is charge given by the PMOS. NMOS took all that charge. Okay. This was the extra charge. So this extra charge represents the charge coming from the capacitor. So if you are just given the current characteristics, you can find out the capacitance that is connected on the load. Are you able to see this?
Yes, I did take you.
The capacitance was initially charged somewhat, or what? How is that charge left out, which the capacitor is just producing afterwards? That I'm not understanding.
So the way to bataya na, the NMOS will continue to remain in saturation region for a longer duration of time. And only when capacitance discharges, it will go into linear region. So then its current would discharge.
Sir, would doubt